Function is normally sinusoidal is no problem. Sinusoid gradually increase, gradually down. So especially that square wave. Square waves are very steep input. As well as a square wave input, how the output will happen. So this is that we can study. So this is for the operational amplifier. You got the operational amplifier here. This is op amp. Input is a square wave. So input is a square wave. Square wave means very steep. So this is for the step change input. So this is the input is the step change in input. So this is the input waveform. Input waveform is a very step change. So this is a VI. So VI is a very instantly increase, instantly down. So this is for the square wave. Square waves are the very instantly recently down. So in this case, output wave, how the output wave happen? Output wave is because of this one, output will not instantly follow the square output wave like this. Maybe try with like this way. Cartesian shape. So this is the output. Output, so this is D and this is a VO. Input waveform is square wave, output waveform you can see like this. So this is the slew rate. Slew rate means the change, how fast the output voltage of the operational amplifier can change for the step change at input. So this is if we got the time delay. So this is the delay. This is related to the slew rate. Because of the input instantly reset, but output will not instantly. It's wait for some time. So this is the delay. Delay time is that we can also call it the slew rate. So this slew rate is the definition. Then slew rate. Specification. Operational amplifier shows how fast the output voltage of operational amplifier can change for step change at input. So this is we call a slew rate. Slew rate means that the slew rate is a specification of an operational amplifier shows how fast the output voltage of the op amp can change for a step change at input. So this one we also got as a equation. Slew rate equal to maximum change in VO. Maximum change in VO. VO in the output voltage divided by change in die. So this is the equation we can calculate for that utilize for the slew rate. Slew rate means that maximum change in VO divided by change die. So this is the slew rate. So this means that even you put the input is a step waveform, square waveform, output will delay. Output take the time delay to change. So this is the slew rate. Okay, this programs are 2 volt peak to peak square wave at the frequency 50 Hz applied to the voltage follower, which is slew rate. Slew rate is a 0.5 volt per microsecond. So this is the 2 volt peak to peak. So this different way is a 2 volt. So this one is the frequencies are applied to. This is frequency at 50 Hz. F is a 50 Hz. So you can calculate period. Period T is 1 by frequency. So the 1 by 50. So 1 by 50, you got that a period. So this period will be that 50 is a kilohertz. So the frequency is 50 kilohertz. 50 hertz is 50 into 10 power 3. So then you can calculate the time. So time will be the microsecond. So this is you can change to micro. So this is 10 power 6 divided by 50 into 10 power 3. So this is microsecond. So this one you can calculate. So there's a microsecond. What you got is this is a 20 microsecond. So microsecond, 20 microsecond. This is the period of the waveform. And 2. You also have to calculate the time taken to change by 2 volt. In this case, you have to use this equation. Slew rate is equal to maximum change in VO divided by change time. So this is we can use the equation. Slew rate equal to maximum change in VO. So this is delta VO. Maximum change in VO divided by change in time. So delta T. Delta T change in time. So that here is given a slew rate. Slew rate is the 0.5 volt per microsecond. Okay, the change voltage is 2 volt. So you have to calculate that delta T. Microsecond is required to change the slew rate. Okay, now I talk about the slew rate for the square waveform. Square waveform slew rate because the square wave output will be the trapezoidal side. Input is a square, but output will not be square. So a little slope here. Another point is that we also follow the sinusoidal. If you supply the sinusoidal, what will happen? And normally we use that kind of amplifier. This is for the follower circuit, the negative positive. That this and this combine. So this is the output V0, and this is for the input is the Vn. So input will be the sinusoidal voltage, sine wave. So this is input. But output will be not exactly sine. It will like this. So this is the output. So input is sinusoidal, output is at this phase because this one with the slew rate. So because of this one, we can also calculate this limitation. This also output waveform will be the limited. So we can use any frequency. If you take will be the some frequency rate. Input is sine wave, output should be sine wave. But frequency should be limited. If you put this higher frequency or there's a higher frequency, then will be distorted waveform will be coming out. So the input is a sinusoidal, output is limited. You can put any input. If your input frequency higher than the limitation, output sine wave will be distorted. So this limitation frequency, acceptable maximum frequency can be calculated. That equation is slew rate divided by 2 by V0 maximum. So this is the equation. So this is the maximum allowable frequency to be utilized for the operational amplifier without happening the slew rate. So this equation is F maximum is equal to slew rate multiplied, slew rate divided by 2 by V0 maximum. So this is for the limitation for the sinusoidal circuit. So this program, the slew rate of the 741 IC. So this is an operational amplifier. This is 0.5 volt per microsecond. So it's configured as a voltage follower. So this is utilized as a voltage follower and maximum frequency. So maximum frequency that can be operated from the circuit. So the 20 volt P2P sine wave and 2 volt P2P. So we have to calculate maximum frequency. So we have to use this equation. F maximum is slew rate divided by 2 by into V0 maximum. So this equation we use. So the equation is we use here. F maximum is equal to slew rate divided by 2 pi into V0 maxima. So the equation is slew rate divided by 2 pi into V0 maxima. So we substitute. So the slew rate is a 0.45. So this substitute 0.5 divided by 2, 3.1416. So V0 maxima. All that are 20 volt P2P sideways. So you have to get 20 volt. So this one is a you calculate. So this is a slew rate is 0.5. So this one 1 microsecond. So this is for the 1 microsecond. So 1 microsecond is equal to 10 power 3 milliseconds. So 0.5 into 10 power 3, 2 into 3.1416 into 20 milliseconds. So this is a microsecond. So 10 power 3. So this is a kilohertz. So this one your unit will be the kilohertz. So you solve this one. So you will get it at 7.96 kilohertz. So this is for the sub A. And B also the same as maxima. Is equal to the voltage will be also 0.5. So divided by 2 into 3.1416 multiplies the voltage with the delta. We use the PI sample. 20 volt. 20 volt P2P means this is a P2P voltage. 20 volt. But you have to substitute the 10 volt. So this is a 10 volt. Your P2P here, but here change is half. So you have to substitute 10. Similarly, 2 volt P2P. 2 volt P2P means this voltage is 2 volt. But you only have to substitute the 1. So this is for the 1 volt. Only this one you have to substitute. So this one also the 1 microsecond. So this is a 0.5 into 10 power 3 divided by 2 into 3.1416. So that one you calculate is as 9.6 kilohertz.
So using training.
This one is 10. Okay, this one is a close to gain is 150 and unity gain bandwidth is at 2 megahertz. We have to calculate the bandwidth. So this is for the you can calculate. So AV closed loop multiply bandwidth is equal to unity gain bandwidth. So this is the unity gain bandwidth. So this is the unity gain bandwidth. This is UGB. So AV closed loop is the 150. Okay, we don't know the bandwidth. UGB is at 2 megahertz. So you got the bandwidth. So 2 megahertz is 2000 kilohertz divided by 150. Then you got the bandwidth. So the bandwidth calculation is 2000 divided by 150. 2000 divided by 150. So this is at 13.33. 13.33 kilohertz. This is the bandwidth. First problem is we have to calculate the slew rate. So determine the slew rate. So equation will be the slew rate equation is the maximum change in VO divided by change in die. So this is the slew rate. Maximum change in VO divided by change in die. So we calculate change in VO means that VO voltage change 0 to 7. That is 8 microseconds. So 7 volt, 8 microseconds. So the slew rate will be the this we saw so megahertz. So this is the So this began as 7 divided by 8. So this is 0.875 volt per microsecond. 0.875 volt per microsecond. So this is for the slew rate. And this is another problem. The above circuit is a non-inverting amplifier constructed with a 741 operational amplifier. Slew rate is 0.5 volt per microsecond. And unity gain bandwidth is 1 megahertz. So we have to calculate the bandwidth. So this one is we have to use an equation. Bandwidth of the circuit. Bandwidth of the circuit is this equation you have to use. AV multiply bandwidth is equal to UGB. Unity gain bandwidth. So this one. So that here is the bandwidth. We don't know the bandwidth. So unity gain bandwidth. So unity gain bandwidth. So this is also equal to the unity gain bandwidth. Input voltage is 0.5 volt microsecond. This is input voltage. We need to calculate the output voltage. So how to calculate the output voltage? This equation we have to use as a formula. So I give you the formula. So this one for the the output voltage we can calculate VO is equal to the V1 RF by R1. So this is the V4. So the output voltage through you can calculate RF is here 220. R1 is at 2. So this is a VO. So this is for the VI, this is the VO. So this is where we can calculate VO by VI is the AV. So this is 110. So you can substitute the AV. So here you given the unity gain bandwidth. So this problem also given the unity gain bandwidth. So unity gain bandwidth is 1 megahertz. Yeah, also unity gain bandwidth is 1 megahertz. So that you substitute here, UGB, AV into bandwidth is UGB. So AV is 110, multiplying bandwidth is a unity gain bandwidth, is 1 megahertz. So this is 10 power 3 kilohertz. Then you got the bandwidth. So 1000 divided by 110 kilohertz. So this one you substitute, you calculate, so you can calculate the bandwidth. Bandwidth is equal to 1000 divided by 110. So this is 9.09. So this is 9.09 kilohertz. So we get about 9.09 kilohertz is given. And another one also have to calculate the slew rate. Slew rate given change in time. Change in time is slew rate 0.5 volt per microsecond. So maximum change in output voltage. So this output voltage you can calculate, and also you can calculate P2P output voltage. So you have to calculate the P2P output voltage. So input voltage is 0.5 volt. So we have to calculate the slew rate. Slew rate is equal to V0 by change in time. So in this case, this program is also given the change in time. So change in time means that bandwidth is 1 megahertz. So this by 1 megahertz, you have to calculate the time. So time is equal to 1 by f. So 1 by f means that this is 1 megahertz. So this is 1 by 10 power 6. So this is 10 power 6 microsecond. So this is 1 microsecond. So this is the time you can calculate. Then you can substitute here. Here is the slew rate is 0.5. So 0.5. We don't know the output voltage V0. Change in time is 1 microsecond. So then you got the V0. V0 is 0.5 volt. So voltage is 0.5 volt. So this is for the maximum P2P output voltage. Okay, now I will summarize. Today I give you this operational amplifier. So operational amplifier characteristic. So firstly I give you the frequency response. Frequency response of the operational amplifier. This means that we can use as an operational amplifier for the wide range of the frequency response. So all the amplifier call that they are limited bandwidth. So within that range we have to utilize. If beyond the range, the amplifier will not amplify properly. So this is a response is a frequency characteristic. This frequency characteristic is a wide for the operational amplifier. So that when the operational amplifier is amplifying, there are the two distortions can happen. Amplitude distortion and the phase shift distortion. Amplitude distortion can be caused by the offset DC voltage. This means that inside the operational amplifier, some of the transistors are not equal. So they are not the same. So it will cause the offset DC voltage. So because of this offset DC voltage, the voltage level will be changed. Another one is the phase shifting. Phase shifting also can happen in the operational amplifier. Because the phase shifting, the circuit will not be stable. So because of this one, we have to apply the appropriate balancing circuit. Balancing circuit means that bandwidth compensation. So most of the operational amplifier 741, they are IC already got the internationally compensation circuit. But you want to use the frequency beyond that their specification, you have to attach that external compensation. So that will be the single capacitor or the feed forward compensation circuit can utilize. And I also give you this gain bandwidth product. So the gain bandwidth equation to calculate the bandwidth, to calculate the slew rate, to also be calculated. Another one is the slew rate means that instantly input voltage square wave voltage is raised instantly, but the output voltage is delayed sometimes. Delay for sometimes. So this the time delay is a slew rate. The slew rates can be calculated by the equation. Slew rate is a maximum chain PO divided by chain impedance. So this is a slew rate. And then I saw there's a couple problem involving the slew rate, bandwidth, those things I saw. So this is for the tonight. So the speed control is a primary concern for our main objective of the power electronics. So we control the motor. We control the motor means the motor speed need to be controlled. Now that one is that I will explain you the frequency control. So normal motor speed is we have full voltage, full frequency applied. So this motor we run with the 1,500 RPM. And then with motor speed measurement we can use the frequency flashlight. So this flashlight is also the fast oscillating wave. So normally it's called the 555 timer or something. So this frequency oscillating. The frequency oscillator gives the flashing light. So this flashing light we utilize and we measure the motor speed. And also that this one also includes the frequency, the variable frequency devices. This frequency devices called as switching. So this is a switching the frequency. Those switching mode circuits produce a different frequency. This frequency effect into the motor, so motor speed can be changed. So the motor speed is normally depending on this equation n equal to 120 F divided by P. So n is a motor speed. F is the frequency. P is the number of poles. So we want to control the motor speed. So in this case, what we use is we have to drive the variable frequency. So that this circuit is called as a variable frequency oscillator. So this is the oscillator. So this called as we drive the frequency circuit. So variable frequency. Variables are fast. So fast are the drive as an electronic drive system. So this one is a drive motor. So this is for the variable frequency circuit. So all the electronics drive circuit in the oscillator system, we use the various operational amplifier. Operational amplifier that I give is a basic principle. So also time the switching waveform. So switching waveform means that they produce a variable frequency waveform. So frequency waveform that drive the circuit and then we drive the motor. So because of this one motor control system, we can give you the equation. So this is a basic equation for the motor control A, n equal to 120 F by C. So n is the motor speed, A is the frequency, P is the number of poles. So normally motor speed is the frequency is 50 Hertz, P is a 4 pole, then motor speed n is equal to 120 50 divided by 4. You got there 1500 RPM. So this is the full speed that we'll be running. So in the variable frequency device, we have to provide as a control circuit. So this control circuit will be as a control rectifier. Control rectifier. So this control rectifier is connected to the line 1, line 2, and the line 3. So this is for a 3-phase system. So this is a fixed frequency supply. Fixed frequency supply. Fixed frequency supply is providing the fixed frequency. This is the turbine frequency at 50 Hertz. And so this control rectifier produces a DC output. So DC link. So this one in the SASA, this one the control box, you can see the DC. So this DC is a DC output voltage coming out. So we have to phase down the DC. So this is for the phase down circuit. So we don't want any pulse or any high voltage waveform. So we use a DC circuit, and also we use the inverter. Inverter means that this DC is converted to AC. So here is the AC, now here is the DC. The DC now inverted to AC. So this AC drives to the motor. So this supply to motor. So this is the basis of principle of the control rectifier. So this control rectifier provides the variable voltage. So control rectifier it provides variable voltage. So this inverter provides the frequency control. So this is for the variable frequency. So then the drive the motor. So the inverter is the blue bulb. The whole blue bulb is a combination of the all. So in the blue bulb, you can see the all combination. This control rectifier, DC, inverter, all as a control. So this is for included in the blue bulb. So blue bulb, we include the line 1, line 2, line 3 input. So this is the 41 by 5 volt. Line input. And here is a UVW motor output. So we use a 3-phase motor, line voltage 41 by 5 volts, the 3-phase motor we utilize, so that the whole blue bulb includes the input is a 41 by 5 volt, and then so this all frequency are changed inside the circuit, and then the inverter is a frequency control. So on the knob we can change the frequency and supply to the motor. So this is for the inverter circuit. So this inverter circuit, how we control the frequency? In this case, we utilize a pathway modulated system. So pathway modulated system. We utilize for the frequency control. Frequency and the output voltage control. Pathway modulated system working. Normally now we put a switching. This circuit called the electronic circuit. They call the switching waveform. So I draw you the switching waveform. Switching waveform will be this. They are switching time delay is different. Firstly, the first waveform you got the frequency is very quick, and this one is a longer, and this one will be the longest, and also some more like this. So this one also. So opposite direction also switch give you the opposite direction flow the current. So the flow the current to opposite direction then will be faster and then longer and then so slower. So this kind of switching. Switching means that inside the circuit we got the switching circuit. The switching circuit are switching. Their switching rates are different. So this is inside that this is switching circuit. Switching circuit. They are switching rate are different. This means that you see here from small I show you there's a symbol. Small 0 to 1. 0 to 1 or the 2 to 3, 4 to 5, 6 to 7, 8 to 9. So for example, the 0 to 1 switching side will be the 1 microsecond. 2 to 3 the switching will take for the 2 microsecond. 4 to 5 it for the 3 microsecond. And the 6 to 7 2 microsecond. And 8 to 9 1 microsecond. So we are switching alternatively. So they are for the 0 to 1 switching time is 1 microsecond and 2 to 3 session switching time 2 microsecond. 4 to 5 is the longer one. 6 to 7 so decrease. 8 to 9 also decrease. So that the more the switching, the more output is coming out. So the longer the switching, the more output coming out. So that what you get the draw the circuit is this one here is the switching is small, so voltage is small. Switching that increase, voltage increase, so this will voltage increase. The voltage decrease like this. So this means the voltage will be the changing. The longer the switching, the higher the voltage. So because of by this way, we provide the sinusoidal voltage. So sinusoidal voltage coming out. So this output voltage is a PWM voltage. So that by switching rate, we can create the sinusoidal output voltage. So this is the by switching rate. Sinusoidal output voltage is created. So by switching rate, we can create the sinusoidal output voltage. So this sinusoidal output voltage period is also different. So this is the time. T depend on switching rate, total switching time. Total switching time. Or electronic device. So this is the period depending on the total switching down the electronic devices or frequency is equal to 1 by T. So by this way, by making the switching, you can change the frequency. So this is it. By adjusting the switching rate, of electronic devices, circuit frequency, the output frequency. Can be changed.